क्या हाल चाल है? How's everyone doing today? Welcome to today's session. I am so pumped because today we are going to unlock the absolute magic of light. Seriously, have you ever just stopped and wondered why a pencil looks totally broken or bent when you drop it into a simple glass of water? Or, why a diamond sparkles with such insane, intense brilliance even in a dimly lit room? Well, today I'm going to be your friendly guide through a complete one-shot revision of everything you need to know about the refraction of light. Whether you're reviewing for a big exam or honestly just deeply curious about the physics of the world around you, we are going to break this entire concept down. We'll go from the absolute basics to some really cool advanced stuff. So let's get right into it.
Okay, let's dive right into this with a little thought experiment. I want you to imagine you are driving a car super fast down a really smooth, straight highway. Suddenly, the right side of the car hits a thick, sticky patch of mud on the shoulder, but the left wheels are still on the smooth road. What happens? Does the car just slow down in a perfectly straight line? No way, right? It violently swerves. It changes its path. Because one side of the car slowed down before the other side, the whole direction of the vehicle shifted. It turns out, this sudden change in speed, causing a sudden change in direction, is the exact, perfect analogy for how light behaves when it hits a brand new environment.
And honestly, that brings us right to the core definition: refraction. What is it? It's simply the phenomenon where light changes its path, or, bends, when moving from one medium to another. And why exactly does it bend? Because of a sudden change in its speed. It is absolutely crucial to understand here that this bending doesn't just happen gradually over time as the light travels. No, it happens precisely at the boundary, the interface where those two different mediums actually meet. Just like that car hitting the edge of the mud. The very second light hits a medium where it has to travel at a different speed, its path shifts.
So here is our quick roadmap for today's explainer. First, what is refraction? Second, Snell's law. Third, glass slabs and thick mirrors. Fourth, prisms and bending light. Fifth, real versus apparent depth. And finally, the really cool stuff, total internal reflection. All right, starting with section 1. What is refraction? Let's get the basic rules of bending down.
I want you to imagine a beam of light traveling completely freely through empty air, and then, boom, it suddenly dives into a solid block of glass or maybe a really deep pool of water. It hits that boundary and suddenly the rules of the road change entirely. Let's walk through this table together because honestly, it is the foundation of everything we're going to talk about today. It all comes down to two types of mediums, rarer mediums and denser mediums. Think of a rarer medium, like air, as an empty, wide-open highway. The speed of light here is very, very high. But a denser medium, like glass or water, that's more like a crowded city street. The speed of light naturally has to drop. Now here is the absolute golden rule you must remember for your exams. When light goes from a rarer medium to a denser medium, meaning it goes from moving fast to moving slow, it bends towards the normal. And the normal is just an imaginary perpendicular line we draw right at the surface boundary to help us measure things. Conversely, when light escapes from a denser medium back out into a rarer medium, so it goes from slow back to fast, it bends away from that normal line. So the bending direction depends entirely on its speed in that specific medium. Oh, and here's a very quick revision point for you. What if light comes in exactly straight down, like right along that normal line at an angle of 0 degrees? Well, it just slows down, but it goes straight through. Completely undeviated. No bending at all.
Moving on to section 2, Snell's law and refractive index. This is the math behind the magic. Now that we know the basic rules of how light bends, let's look at the mathematical rules of the game. And please, don't worry, it's actually very straightforward. Snell's law is a beautifully simple mathematical constant. It simply states that the sine of the angle of incidence, that's the angle the incoming light ray makes with our imaginary normal line, divided by the sine of the angle of refraction, which is the angle the newly bent ray makes, always equals a constant number for any two given materials. And we call this specific constant the refractive index. You'll often see it represented by the little Greek letter mu. Basically, you can think of this refractive index as a measure of speed. It compares the speed of light in a complete vacuum to its speed in that specific new medium. So, if a material's refractive index is really high, it means the medium is very dense and light is going to travel incredibly slowly inside it.
For example, look at this specific number, 2.42. I am always so excited to share this one with my students because 2.42 is the refractive index of a diamond. This is literally the highest refractive index of any common natural material on Earth. Because this number is so massively high, it means light travels at its absolute slowest when it's inside a diamond. This intense slowing down is the big secret to why a diamond bends light so drastically, which we are going to revisit in a super spectacular way at the end of this session. So, keep that number, 2.42, locked in your head. Section 3. Glass slabs and thick mirrors. Let's see how light actually shifts in the real world.
So let's shift our focus to real-world objects. What actually happens when light hits a plain, flat, rectangular piece of glass instead of just a single surface? Well, when a ray of light goes through a plain glass slab, it enters the glass, which is a denser medium, right? So, according to our golden rule, it bends towards the normal. But then it reaches the bottom side and exits back into the air, which is a rarer medium, so it bends away from the normal. Because the top and bottom surfaces of the slab are perfectly parallel, an amazing thing happens. The final exiting light ray is perfectly parallel to the original incoming ray. It hasn't actually changed its overall direction, but it has been physically shifted to the side. We call this sideways step lateral displacement. And this brilliantly illustrates the 4 key factors that control just how big that shift is going to be. It depends on the thickness of the glass slab, the initial angle of incidence, the refractive index of the glass itself, and even the wavelength or the color of the light you're using. Basically, a higher thickness and a higher refractive index will always give you a much bigger sideways shift.
Now let's look at a really cool everyday optical illusion using this same concept. What if that glass slab has a shiny silver coating on the back, basically making it a thick mirror? Have you ever looked into a really thick mirror and noticed it creates a faint double image of you? Let's break this complex process down step by step. You see, any glass surface does a little bit of reflection and a whole lot of refraction. So in step 1, when light hits the mirror, a tiny minority of that light reflects right off the front transparent glass surface, and that creates a very weak, dim first image. But the vast majority of the light refracts and enters the glass. In step 2, this massive bundle of light travels straight through the glass, hits that silvered back surface, and perfectly reflects. Finally, in step 3, it travels back up to the glass and refracts back out into your eye. Because the second exiting ray contains the absolute majority of the original light, the second image it creates is by far the brightest, sharpest image you see.
All right, moving into section 4, prisms and bending light. This is where things get a little triangular.
I absolutely love sharing this funny, super memorable mnemonic from our source material to help you remember exactly how a prism works. Baby coal base passande. Basically, for those who don't know, it translates to the baby likes the base. Now, what on earth does this have to do with physics? Well, a triangular glass prism will always bend the incoming light ray down towards its thicker base. Because the two surfaces are angled relative to each other, the light bends down towards the base when it enters the glass, and then, because of the angle on the way out, it bends towards the base again. It's a complete double whammy. The prism forces the light to deviate downwards towards that thick bottom edge. So if you ever get confused on a test, just remember, the light ray acts exactly like a baby. It always goes for the base. But we also have to keep in mind, not all prisms bend light by the exact same amount. The material composition of the glass is everything. Let's briefly contrast 2 common types of glass used for making prisms. We have flint glass on one hand and crown glass on the other. Flint glass has a significantly higher refractive index. And what did we learn earlier about that? A higher refractive index means it slows the light down much more drastically, which directly results in greater bending or deviation of the light ray. Crown glass, however, has a relatively lower refractive index, resulting in lesser light deviation. So just by mixing different materials when they're manufacturing the glass, scientists and engineers can actually control exactly how much the light is bent.
Section 5, real versus apparent depth. Let's talk about optical illusions in the water.
So let's see how all this math and bending builds into an optical illusion we have probably all experienced. I want you to picture standing right at the edge of a crystal clear swimming pool. Have you ever noticed how the bottom of the pool looks way shallower than it actually is? You know, you might step in expecting the water to be up to your knees, and suddenly you are soaked all the way up to your waist. Let's do a quick interactive quiz taken straight from our source's numerical examples. Imagine a coin is resting flat at the bottom of a container filled with some clear liquid. Let's say the actual real depth of the coin is exactly 20 centimeters, but when you look straight down into the liquid from above, the coin appears to be floating at only 15 centimeters deep. So my question to you is, why does this liquid magically lift the image of the object up by 5 whole centimeters? Take a second and think about the light rays leaving that coin.
Okay, did you figure it out? The answer is mathematically beautiful, and the formula to solve it is beautifully simple. It's all because of refraction. The light rays bouncing off the coin have to travel up through the denser liquid, When they hit the top boundary and enter the rarer air, they naturally bend away from the normal. When your eyes and your brain capture those newly bent rays, your brain automatically assumes that light travels in a perfectly straight line. It doesn't know the light bent, so it traces those bent rays straight backward to a convergence point much higher up. Mathematically, the apparent depth equals the real depth divided by the liquid's refractive index. So if that liquid happens to be water, which has a refractive index of roughly 4/3, you simply take the real depth of 20, divide it by 4/3, and boom! The math proves that the virtual image is lifted perfectly to 15 centimeters. And by the way, that 5 centimeter difference between the real and apparent depth, that's known as the normal shift.
All right, Section 6, Total Internal Reflection. This is where we learn how to trap light.
And now, my friends, we have arrived at the ultimate climax of this entire explainer. This is the spectacular phenomenon where light completely refuses to leave a medium. Let's break down exactly how this magic trick works. To really understand this, we first need to define a very delicate balancing point called the critical angle. Imagine you're holding a waterproof flashlight underwater, and you're aiming it up towards the air. Light is going from denser water to rarer air, so as we know, it bends away from the normal. As you tilt your flashlight further and further to the side, increasing the angle of incidence, the exiting ray bends closer and closer down to the surface of the water. Eventually, you will hit a very specific angle of incidence where the refracted ray bends so much that it doesn't even enter the air at all. It perfectly skims the surface at exactly 90 degrees. That specific incoming angle is the critical angle. For a standard glass-to-air boundary, this magic angle is roughly 42 degrees.
So, the crucial million-dollar question is, what happens next? Let's say you're in glass, and the critical angle is 42 degrees, but you tilt your flashlight even further. You go to 45 degrees. What occurs when light hits the boundary steeper than the critical angle? It simply cannot bend past 90 degrees and still be considered refracting out of the material. It is literally run out of room. So what does the light do?
Here is the incredible payoff: total internal reflection, or TIR. When the angle of incidence exceeds the critical angle, refraction completely dies. It stops existing. Instead, the boundary instantly acts like a perfect, flawless mirror. 100% of the light totally and internally reflects right back down into the denser medium. Not a single solitary photon escapes into the air. And this brilliantly illustrates how modern optical engineers use glass prisms instead of standard mirrors in high-end optical instruments like submarine periscopes and high-quality binoculars. By carefully cutting a prism, we can actually force the light to hit the internal glass-air boundary at an angle greater than 42 degrees. For example, an isosceles right prism can be set up so light hits the inside wall at exactly 45 degrees. Boom! Total internal reflection. We just bent the light a perfect 90 degrees incredibly efficiently without needing any silver mirror coating. You can even use that exact same prism from a different angle to bounce the light twice, creating a full 180-degree U-turn. Or you can use an equilateral prism where all the angles are 60 degrees to bend the light exactly 60 degrees. It is perfectly predictable, 100% efficient optical engineering based entirely on manipulating these angles. Which perfectly brings us full circle to exactly where we started our session today: the diamond secret. Do you remember back in Section 2 when we talked about how a diamond has a massive refractive index of 2.42? Well, there's a mathematical inverse relationship between refractive index and the critical angle. Because the refractive index is so high, a diamond's critical angle is incredibly tiny. It's only 24.4 degrees. This means the escape window for light inside a diamond is extremely narrow. Almost any light ray that enters a diamond ends up hitting the inside walls at an angle greater than 24.4 degrees. Because of this, the light gets completely trapped. It suffers repeated total internal reflections, bouncing wildly all around the inside of the stone before it finally finds a tiny mathematical window to escape back out to your eye. That trapped, constantly bouncing light is exactly what creates a diamond's brilliant, captivating sparkle. Seriously, isn't that just mind-blowing? Light literally gets trapped by its own physical rules. So, as we wrap up this explainer, I want to leave you with this final provocative thought. Knowing exactly how light gets totally internally reflected and trapped inside a medium, where else in your daily life do you think this incredible phenomenon is at work right this very second? Hint, think about the glowing fiber optic internet cables buried deep underground that are literally carrying this very lesson to your screen right now. Thank you all so much for joining me on this deep dive into the absolute magic of refraction. You guys have been amazing today. Keep wondering about the world, keep revising those critical angles, and I will definitely see you in the next session.